Okay, welcome back, and today we're going to start Introduction to Probability, section excuse me, 7.3. So in this section, it's going to be Introduction to Probability Experiments. How do we define a probability? What is an event? What is a sample space? Was it is an outcome? What is a trial? So we're going to set the scaffolding together. We're going to put the basics and the foundations together to talk about more in-depth look of probability. So if we look at a spinner, a random spinner, we spin the spinner, and this is an example of a probability experiment because we're going to spin the spinner and then see what number comes up. So in this case here, the experiment here is a probability experiment because each outcome is based on a random chance, right? Assuming that it's a good spinner, and each outcome here. Now here's the thing. Now, in this experiment where we're spinning a spinner, and we're going to see what number comes up after we spin it. Okay. So in this experiment, every time we spin the spinner is called a trial. And each trial can result in one of three outcomes. We could either get a 1, a 2, or a 3. Okay. And let's see. What else? So those are going to be the outcomes. Now the sample space, by definition, is the set of all possible outcomes in an experiment. So in this case, the sample space is the numbers 1, 2, and 3. Okay, because no other outcomes can happen on one spin of a spinner. So that's the sample space. So again, this is based on this idea of a set notation, set theory. Okay, so we know that the set of all possible outcomes is the sample space. Okay, a trial is one repetition of the experiment. Okay, so we spin the spinner one time, that is one trial. Okay, now we can define trials in different ways. Like we could say, okay, let's spin the spinner 5 times, and we'll call that a trial. So every time we spin the spinner, we're going to spin it 5 times, and we're going to record the 5 numbers that come up and the order in which they come up. So that could be a different type of experiment. But in any case, it's still a probability experiment. So different nonetheless, but it is still a probability experiment. So there's events. Now events are sets of outcomes that we define. Like I could define the event that I get an odd number on one spin of a spinner. Okay, so that means if either a 1 or a 3 come up, then that event has occurred. Okay, so an event is a defined set of outcomes. It could be one outcome, or it could be a set of multiple outcomes that give me the event. Okay, so events are normally represented by capital letters. Okay, and again, it's a set of outcomes. An event is a set of outcomes. Now you could have a simple event, which consists of a set of only one outcome, or you could have a compound event, which would be an event that has multiple outcomes that can get it. Okay, so if there's more than one way to get the event, then it's a compound event. If there's only one way to get the event to occur, then it's a simple event. Okay, let's see. I think that's all I want to say at this point. Now it says 2 coins are tossed, and a head or a tail is recorded for each coin. Give a sample space where each outcome is equally likely. Okay, so what does that mean? Equally likely means that every outcome has an equal chance of occurring. Okay, or in other words, each outcome has the same number of ways of occurring. Okay, so that's another way of looking at it. Okay, so now in this case here, we're flipping 2 coins, and we could get a heads or tails on each coin. So what could be a sample space, right? What the sample space again being the sample, the set of all possible outcomes. Okay, so the easiest one is just to record the what you get on the first coin and what you get on the second coin. So you could get a heads, heads. You could get heads, tails. You could get tails, heads, or you could get tails, tails. So you've got 4 outcomes you can get. Now, each one of those outcomes only has one way of occurring. Okay? You can only get heads on the first flip, tails on the second flip, or excuse me, heads on the first coin, tails on the second coin, one way, right? So each one of those outcomes, each one of those 4 outcomes only has one way of occurring, and therefore they are equally likely events, okay? If one event out of the sample space was more or less likely to occur than the other outcomes, then it would not be equally likely. Okay, and so here's our sample space. So if we use H as heads and T for tails, then we can represent all of the 4 equally likely outcomes represented by each one of these symbols. And you notice that there's only one way to get a heads and a heads. There's definitely only one way to get a tails and tails. There's only one way to get heads, then tails, and then there's also only one way to get tails followed by heads. Okay. Okay, 2 coins are tossed and a head or tail is recorded for each coin. Write the event E. The coins show exactly one head. Okay, so now how would we write the event? Again, in set notation, because remember, an event is a set of outcomes. How would we write E, the event E, to show exactly one head, the event of getting exactly one head? Well, how many ways can I get one head on the flip of 2 coins? Well, there's 2 ways. I get heads on the first coin, tails on the second coin, or I get tails on the first coin and heads on the second coin. So the event E would be represented by the set of these 2 outcomes. So out of the sample space, if either one of these 2 outcomes occurs, event E has occurred. Okay. So the set operations for events. So now this is where we're going to now take what we learned in section 1 and apply it here in section 3. It says let E and F be events for the sample space S. E and E intersect F occurs when both E and F occur, which means that an event and an outcome from E, right, set E, and an outcome from F have occurred. Okay, so E intersect F means that both the event E and the event F have occurred. Okay, E union F means that it is when either E or F or both have occurred. Okay, so this is E union F means either or both. The intersect F is when both E and F occur. And then E prime occurs when E does not occur. So it's everything that is not an E, right? So the complement of E is when E does not occur. Okay, so it's if anything else but E occurs, well, not E has occurred, right? Now, a study of workers earning the minimum wage grouped such workers into various categories, which can be interpreted as events when a worker is selected at random. So if we use a random process and we select workers at random, then we can look at these wage groups as events. Okay, so now the Economic Policy Institute, so this is where the source of the data. Okay, says consider the following events. E is that the worker is under 20. F is that the worker is white. G is that the worker is female. Describe the following event in words. So what does this mean? So again, going back to our set notation, this is not E intersect not F. So in other words, this is not E and not F. So in the sense of probability of an event is that both of these happen. So the event of not E and not F. So what is not E? That means the worker is not 20. Not F is that the worker is not white. So it says this is the event that a randomly selected worker is both at least 20 and not white. Okay. Okay, and that's what we got. Now, let's talk about mutually exclusive events. Again, events are sets. So what do we mean by mutually exclusive sets or disjoint sets? Well, that means they're empty. The empty set, right? If they're disjoint, if they're mutually exclusive events, that means their intersection is empty. There's no overlap. And so the intersection, like we saw in section 1, is the empty set. Okay, so here we go. So we've got these two events. Okay. And so let's say we're rolling a die. And so we event E. Event E is that we have an even, or excuse me. Okay, well, event E is that we get a 4, 6, a 5. So 4, 5, or 6. That's event E. If any one of those occur on one roll of a die, E has occurred. G is the probability of getting 1 or a 2. Okay, and so this is our sample space, right? So all of the outcomes in the sample space are represented. And so we get a 1, 2, 3, 4, 5, or 6. So that this is S, and we would have an S up here for the sample space. Okay, so now in a Venn diagram, we would have a U for the universe. But since we're talking about probabilities, we're going to talk about sample space. And so this would be S is the sample space. And notice that the intersection between E and G, there is no overlap, right? There's nothing in common here. So the intersection is 0. Okay, so this would be an example of two mutually exclusive sets, two mutually exclusive events. Now, the basic principle of probability. This is one of the definitions of probability. This is the if you have a sample space and you know the sample space, the way to calculate probability is very easy. You take the number of outcomes that give you E, and you divide it by the total number of possible outcomes in the sample space. That is the definition of the probability of an event. The number of ways of getting that event to occur divided by the total possible number of events, or excuse me, outcomes. Okay. And so again, we're using our cardinality notation here because these are sets, right? So this is the definition of probability. Okay, the probability of an event is equal to the number of outcomes that give you the said event divided by the total number of outcomes in the sample space. So now suppose a single fair die is rolled. Use the sample space of 1, 2, 3, 4, 5, 6. Find the probability of event H, which is defined as that you rolled a number less than 5. Okay, so what's the probability of rolling a number less than 5? Okay, so ask yourselves, okay, use the definition of probability. How many ways can I get a number less than 5 on one roll of a die? That's right, 4. Right? I can get a 1, 2, 3, or a 4. Okay. Now, how many possible outcomes are there? Well, there are 6. So by the definition of probability, the probability of rolling a number less than 5 is 4/6, or 2/3, or 0.6667. Okay. 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 Good. Okay. Let's talk about a standard deck of cards. Now, a standard deck of cards has 52 cards. Okay. There are the aces, or well, I would call them the number cards, right? Or you could split it up into aces, and then the number cards are 2 through 10. But again, we're not going to split hairs. So we have the aces, and then we have the number cards, which is 2 through 10. And then we have the face cards, which is Jack, Queen, and King. And then you have 4 suits. The suits are the hearts, clubs, diamonds, and spades. You also have black cards, right? And you have red cards. So that is pretty much all you need to know for a standard deck of cards. So each suit has 13 cards. You have 9 number cards, 1 ace, and 3 face cards, which make up the 13 cards of each suit. And the 13 cards of each suit add up to the 52 cards in a standard deck. Oh, look at that. And we are on slide 52. Whoa! Anyway, find the probability of drawing a jack or a king. Okay, well, how many different ways can I get either a jack or a queen on one draw? Okay, well, how many jacks are there? There's 4 jacks. How many kings are there? There's 4 kings. So how many different ways can I get either a jack or a king or both? Can I get both in this case? Is it possible to get a jack and a king on one draw? No, of course not. These would be, what would we call these type of events? Well, and in fact, we could look at these two as events. We could look at getting a jack as one event and getting a king as another event. So we could look at the event of getting a jack and the event of getting a king on one draw. So we could say these are 2 events. We could call that event J, and this is event K. And so we could look at this as an OR statement, okay? And they're mutually exclusive, right? These 2 events are mutually exclusive. So how many ways can I get a king? 4. How many ways can I get a jack? 4. Well, how many different ways can I get a jack or a king? Well, you just count them up, right? The union. So you have 8 ways of either getting a jack, a king, or both. And so now how many possible outcomes are there for drawing one card? So in other words, what's the sample space in this experiment? I'm drawing one card from a standard deck of cards. How many different outcomes are there for drawing one card? 52. There are 52 different cards in the deck, so there are 52 different outcomes from the sample space. And so now if I want the probability of drawing a jack or a king, then it becomes a very simple division problem. I take the number of outcomes that will give me the event, in this case, the event of either getting a jack or a king, okay? So this would be a compound event, a connected event, because of the OR statement. Okay, so in other words, the probability of getting a jack or a king would be 8 out of 52. Or in other words, it would be 2 out of 13. And then we could divide and give the decimal. Okay, so 2/13 would be the answer. Now, one thing you have to know about probabilities is that any probability, the probability of any event, whether it's a compound event or a simple event, must always be somewhere between 0 and 1 inclusive, which means it could be as small as 0 or as large as 1. And that's it. So in other words, you cannot have a negative probability and you cannot have a probability that is bigger than 1. Okay, those are the conditions. Okay, and if you think about the definition of a probability, it's impossible to have a probability that's outside of this range. Okay, so let's look at this table here. Okay, so now here we're looking at the data, and we have recreational equipment injuries, and we've got bicycles, skateboards, trampolines, playground climbing equipment, swings, and swing sets. Okay, now notice over here we've got, out of all of the data we've collected, or that was collected for this, these are the numbers out of the total that fall into each one of these categories. Okay, so this is also another type of using another definition of probability, which is what I also call the relative frequency definition of probability, is because now it's based on data. Okay, remember the definition we looked at before is the number of ways of getting a particular outcome divided by the total possible outcomes in a sample space. Okay, so that is the principle of probability, the principal rule, or what I call the theoretical definition of probability, or another way of saying it is the classical definition of probability. Here, whenever we're given data, this is actually called the empirical definition of probability, and it's very, very similar to the classical. Okay, it's the number of trials that give you a particular outcome divided by the total number of trials. So in this case, the trial is each individual injury, right? Okay, and that's what we're looking for. So the number of people, the number of injuries. Okay, so now based on this table, we can calculate a probability that if we randomly selected an injury, we can say, hey, what's the probability that the injury was caused or happened during playing on a trampoline, or was caused when you were playing on climbing equipment or riding a bike, and so on and so forth. So in this case here, if I said, okay, what's the probability of a randomly selected person from this population what's the probability that their injury was caused by skateboards, or caused by, or was caused or happened during riding a skateboard or skateboarding? Well, what we would do is we would take the number of outcomes from this sample, from this data set, the number of outcomes that resulted in injuries during skateboarding. Well, what would that number be? Well, it would be 143,682. And then what we would do is we would divide it by the total number of trials in our sample space. And in this case, what's the total amount of data? What's the sample set? What's the sample size? Okay, so we're going to add up all of these numbers. Okay, and so what would these numbers all add up to? So you've got, what do we got here? We got 700,000, right? 750, 820, 870, right? So 870,000, 878, 885, 893, 902. So 902,000, 903,000, 904,000, 904,600, right? and then you just keep adding. So 904,600, 700, 800, 870. So again, then you add these here. So the point is you're going to add all of these together. That's going to be your total. So then all you have to do is to find the probability that a randomly selected injury or randomly selected person that was injured in this population, that the probability that that injury happened during skateboarding is going to be this number divided by the total sample size. And that is how you would calculate the probability in using what I would call the relative frequency definition of probability based on data. Okay, so there are two definitions of probability we can use. The first one we introduced in this section was the classical definition, which is the number of outcomes that give you a particular event divided by the total possible outcomes in the sample space. And then there's the empirical definition, or what I call the relative frequency definition, which is based on data. And you take the number of outcomes, the number of data that fall into that category divided by the total sample size. Okay, and that is it. So next time we are going to go on and we're going to talk about probability, and we're going to talk about probability rules and how to calculate probabilities and how this all works. So until next time, make sure that you are practicing. Go over these examples. Make sure you know how to do these examples without looking. Make sure you do some exercises in the back of the at the end of the section. Do some of the other try-its, your turns. Okay. And again, if you get stuck on something, or if you don't know what to do, or you're confused by something in the video, write the question down. If you get stuck, bring that question up in class and we'll work it out together. And again, until next time, have a great day, and I'll talk to you later. Bye-bye.